Phoebe Lewis, the supplemental instructor for Dr. Quinn's Natural Science Biology 1 course at Langston University. I've compiled a series of review videos, and this one focuses on Chapter 6. Now remember, Chapter 6 discussed thermodynamics, potential energy versus kinetic energy, ATP, endergonic versus exergonic reactions, and coupled reactions, and enzymes. Now as a review, remember, thermodynamics is the study of energy. There are two laws of thermodynamics that we discussed in Biology 1. The first one says that energy can never be created nor destroyed. It is merely transformed from one form to another. The second law of thermodynamics states that the world has a tendency to go from more order to less order, so towards increasing entropy or disorder. And just a reminder, entropy is the scientific term for disorder. The first law of thermodynamics, remember, it states that energy can never be created nor destroyed. It's merely transformed from one form to another. This figure displays this very well. So what we have here is coal. The coal is burning. So the chemical bonds in the coal, when it's burning, it gets transferred into heat energy, and also it gets transformed into mechanical energy because the water has heated up and has served as mechanical energy to spin this piston, and then it is released also as steam. And so what you have here is just a transfer of energy. And the energy is never being created nor destroyed. It's just being transferred from one form to another. And so when energy is transformed from one form to another, you also you're transferring energy as heat. And so when you transfer energy as heat, you're affecting the efficiency of the particular system. The second law of thermodynamics states that the world has a tendency to go from more order, as in the stack of cards, to less order when you drop the stack of cards. So when you drop a stack of cards, it's not going to stay in this neat little deck that it was in before. It's going to scatter all over the place. And so that is going to go from more order to less order, or towards increasing entropy. Thermodynamics. Let's see if you understood these concepts. Which law of thermodynamics illustrates the following scenarios? A deck of cards scattering as they fall to the ground? Well, of course, that is second law of thermodynamics. We just discussed that. Plants undergoing photosynthesis. This is a more difficult one, so let's think about this. What is photosynthesis? Well, photosynthesis is the process in which plants use energy from the sunlight and convert that into chemical energy that they store in their own sugars. So plants are able to make their own foods or their own sugars by using sunlight. That is a perfect example of the first law of thermodynamics. Energy is never created nor destroyed, it's only transformed. So let's see if we understand the concept of entropy. Which has the least amount of entropy? Let's make sure we read that question correct. The least amount of entropy. An ice cube, which is solid. So in solids, remember, the molecules are well ordered and are confined and packed together. So ice cube is a solid. It has molecules that are packed together and well ordered. Liquid water. The molecules are spaced further apart and they can move past one another, which causes them to be liquid. And steam, the molecules are far apart, which cause them to be a gas. And so gas has the most entropy because the molecules are far apart and are able to move past one another. So it's the most disordered. The liquid water has the next amount of entropy, next highest amount of entropy, and of course the ice cube has the least amount of entropy, as the question entails. So which has the least amount of entropy? The ice cube. Potential versus kinetic. Remember, potential is stored energy, kinetic is energy in motion. So let's determine whether each of the following scenarios is a demonstration of potential or kinetic energy. A log burning, of course, that is kinetic. Okay? A rock sitting on top of a hill, that's stored energy, it's potential. A man running, that's energy in motion, so that is kinetic. A piece of wood, the piece of wood is not burning, it's just sitting there. That's potential. A loaded gun, that is another example of potential energy, stored energy. ATP is the energy currency of the cell. So remember, ATP, adenosine triphosphate, is the energy currency of the cell. So this is how, basically, the energy money of the cell. This is how the cells get their, or use their energy in the form of ATP. So how does ATP work? Well, when the third phosphate group of ATP breaks off, it releases energy in an exergonic or energy releasing reaction. So that third phosphate group will break off. It will release energy to become ADP, or adenosine diphosphate, that only has two phosphate groups. Well, it requires energy to put a third phosphate group on an ADP so that it can become ATP again, and that would be an endergonic reaction, applying that third phosphate group to ADP to make it ATP, so that would be an endergonic reaction. So let's just do a quick review. ATP, adenosine triphosphate. Look at the prefix tri. It has three phosphate groups. That tells you that right there. Adenosine diphosphate. Again, look at the prefix di. It has two phosphate groups. So you can kind of see, look for clues in your answer choices, and it tells you right there, di 2 tri 3. Coupled reactions. Well, coupled reactions just occur when an exergonic reaction powers an endergonic reaction. So the example that's given right here is that you have glycogen, which, if you remember correctly and look at your chart from chapter 3, I believe, glycogen is a polysaccharide. It's nothing more than a long chain of glucose molecules. So when those glycogen is breaking down into its separate glucose molecules, it releases energy. So energy are stored in these bonds. So when you break those bonds apart and just have your regular glucose molecules, you've released energy, and that's called an exergonic reaction. Well, in the process of a coupled reaction, that energy that we release from the exergonic breaking down of glycogen, we can use that energy to attach the glucoses together again and form glycogen again. And of course, that is an endergonic reaction, and together it's a coupled reaction. So just a rule of thumb, breakdown reactions are exergonic reactions, so energy releasing reactions, where build-up reactions are endergonic reactions. So let's see if we understood this concept. Endergonic versus exergonic. Did you get it? So let's demonstrate whether each of the following are endergonic or exergonic reactions. Glucose coming together to form a glycogen. Look at that phrase right there, to form. To form implies that it's a build-up reaction, so that would be endergonic. ATP becoming ADP. Well, let's look at the structures of ATP. ATP, adenosine triphosphate, has three phosphate groups, whereas ADP, adenosine diphosphate, has two phosphate groups. So to get from ATP to ADP, the ATP has to break down to ADP. So a breakdown reaction is, of course, an exergonic or energy-releasing reaction. Maltose breaking down to glucose. Well, it used our key term right there, breaking down. So we know that that is exergonic. And adding the third phosphate group to ADP to form ATP, we look at that phrase again, to form, implies that it's going to be endergonic or build-up reaction. Enzymes are another thing that we discussed in Chapter 6. Enzymes speed up chemical reactions by lowering the activation energy. So speeding up chemical reactions implies that an enzyme is a catalyst. A catalyst is anything that speeds up a chemical reaction. So enzymes are a type of catalyst that work by lowering the activation energy. And activation energy is quite simple. It's pretty much explained by its name, activation energy. It works by lowering the amount of energy required to start a reaction. So these figures right here demonstrate the way an enzyme works very well. So you have a huge, this is without an enzyme, you see that hill that the guy has to push the purple ball up. Well, how an enzyme works is it basically lowers that hill, or lowers the amount of activation energy required to start the reaction, so it is thus easier to perform, and it goes by faster. So that is how enzymes work. Another thing that is important to know about enzymes is that they are specific to the substrates that they act upon. So, for example, it works like a lock and key theory. Not every key will open up every lock. They are specific to one another. So, for instance, this substrate is whatever the enzyme acts upon. So, whatever goes inside of the enzyme that it's going to be working on. This particular substrate isn't going to work in this enzyme because it doesn't have the same shape. However, it would work, this enzyme would, this substrate would work in this enzyme right here. And so just know that the enzymes are specific to the substrates that they act upon. And so that basically covers Chapter 6, and tune in for Chapter 7 review video.